All right, we are now in a position to start working on what we can do in practice, how we can essentially use likelihood and Bayesian inferences on a set of incomplete longitudinal data, but also on survey data, on multivariate data, etc. Before we do so, I would like to take a look at the simple methods and give a little bit of more evidence why they don't work or don't work well, what the problem is. Okay, so we go back to our initial setting, the arbitrary setting of blood pressure profiles that increase as time goes by, and where some drop out earlier rather than later. So, in a nutshell, just putting on informally with the profile still shown, or if you wish, with the profiles taken away. If you do a complete case analysis, you throw away everything at the top, CC here, and you calculate the mean just from the bottom profiles. In this case, it tells us you're completely in the wrong location. In another setting, in another data set, you can be in the wrong location, you can be completely wrong, incorrect regarding the slope, all sorts of features may go wrong. That's one thing. Second, LOCF. LOCF says, okay, if this is your last measurement, you carry it forward till the end of time, and where you're analyzing that last measurement. But if you want to do a longitudinal analysis, you will see that the profile file all of a sudden, in this case very acutely, changes direction, and you will get the wrong impression, not just about the slope, but even about the linearity or non-linearity of the profile. Okay, so LOCF being an imputation method we don't like. CC being a throwaway method, a deletion method, we don't like. What sometimes is done is an available case analysis, and that seems good at first sight. It seems the only thing we can do if you don't like deletion or imputation, yet there are problems and it's not the only alternative left. So in an available case, you say, let me calculate the means at each one of the time points. So here and there until here, because I'm using all the data, available case. But from that moment onwards, only the bottom group is available, so it means the mean will revert to what I have left at the bottom. Okay, I'm using all the data, nothing but the data, I'm not making anything up. So it looks even worse, because I have not just a bending profile, I have a totally broken profile. Nobody in their right mind is going to think that this is a typical evolution of blood pressure. You increase, but then you drop out and your blood pressure also drops and you start increasing from a lower point. That would be a good thing if it would be possible, right? Better than your blood pressure keeping increasing like that. The thing is, we're not really making use of the data in a very clever way, because we basically say at the time of dropout, at that very last time, we still have the data available, but then it's over. From that moment onward, we didn't even know that these patients were ever there. And that's not true. What were we using at the end of the previous chapter? The predictive distribution. So the predictive distribution says, hey, what I know from these patients from the past will give me some information about what's happening now and in the near future. So the likelihood doesn't say, you're gone, and I don't even remember that you ever were there. That's not what the likelihood says. The likelihood says you're gone, but you will not be accumulating more data, but the data I have, I will use under certain assumptions, missing at random, or later sensitivity analysis, to inform me about the average profile, also taking into account that there is a group in the population not observed right now, but still contributing to the population mean. And that is the MAR, or I could say direct likelihood, or if you do things in a Bayesian fashion, direct Bayesian analysis. Okay, so the simple methods. In summary, the complete case analysis is valid under MCAR. Last observation carried forward is not even correct under MCAR, not usually. Why? Well, basically, if you go back, we say, hey, under LOCF, the moment, suppose this is the true profile, but it's unobserved. The moment you drop out, we carry you forward in this way. It's not right. Missing completely at random or missing not at random has nothing to do with it. When would it be valid? Had the profiles been flat after dropout? And that may be very unrealistic, evidently. So LOCF is not even then a correct method. A complete case analysis, there is a problem here. There is a potential fallacy, because missing completely at random, the method is valid, and then some people come to the conclusion, oh, we should use it. Well, no, it's not because a method is valid that you should use it, no. The first thing you do is you look at a good number of methods. You think about, at least methodologically, you think about a number of methods that are valid, and then you pick the best one. For example, in some cases you can estimate a location parameter by a mean. You can estimate it by a mode. You can estimate it by a median. You have choice. Choose the best one. If your data are at risk of being contaminated by outliers, you may choose the median. But in cases you say, no, no question, that's not happening, you may well choose the mean, etc. So you can use judgment, in other words. Well, a complete case analysis is valid under the tight and unrealistic assumption of missing completely at random, but it loses information. So it's a very imprecise, it's a very, in other words, inefficient method. One we shouldn't be using indeed. So, with that in mind, we're going to switch to a simple example, a simple illustrative example that is explained here on the slide, but that I'm also going to write down, so we get an idea of what we see happening here. I'll make a little graph, and then when that graph is made, we will take a look at the slides again and look at the bias here. Okay, so take for example the following setting. Take a situation a bit like before, but now I'll pretend it more continuous. A situation where I have two measurements. Let's call it a pre and a post measurement. Pre the treatment, post the treatment. And then I have people who are in the active group, and I have people who are in the placebo group, for example. So active, placebo. And then we say, yeah, that's true, but that is only the so-called completers group. There is a second group of people who are incomplete. So, for example, there are people who start here, end up there, still in the placebo group, but drop out. I'll indicate that with a D. And then I have people, just to change the direction of the line a little bit, people who start here, end up there, they're the active group, drop out. So I have a 2 by 2 by 2 design. Why 2 by 2 by 2? Well, I have 2 times, 2 treatments, and I have 2 dropout groups, dropouts and completers. So 2 by 2 by 2, that's equal to, as many of us would say, 8. But I'm writing 6, and it's correct again this way. Why do I write 6 plus 2 rather than 8? Well, look at the graph. There are 6 circles and there are 8 crosses. The crosses are all theoretical, design-based means. For example, this is the mean the second time in the active group among the completers. This is the mean in the active group the second time among the dropouts. But the difference is, this mean is observable, that mean is unobservable. So we have 6 observed degrees of freedom, and we have 2 missing degrees of freedom. Okay, let's keep this model structure in mind. Let's return to our slides. And let's build a model around it. 8 means, remember, at least in theory, so I built a model with 4 plus 4 parameters. That's a saturated model. There are people who drop out. This is the time indicator, but the dropouts are only observed the first time. The others are observed pre and post 0, 1. Then I have, to complete the picture, the treatment indicator, capital T, 0 and 1, placebo and active, and I have the probability of being fully observed, and the probability P0, the probability of being partially missing, and the probability of being fully observed. Okay. How we get to the calculations is not so important, but now what we're going to do is the following. We will assume, in turn, missing completely at random and then missing at random. And we will estimate the overall treatment effect, second time, with complete case analysis and with LOCF. Well, what we see is, just to get going, complete case analysis under MCAR produces an unbiased treatment effect. So what we see in the bottom table is not just the treatment effect, it's the bias of the treatment effect. So 0 is good, and we see only 1 0, which tells us that already under missing completely at random, LOCF is biased, which many people don't realize, overlook, but that is the case. Missing at random, sure enough, the CC analysis is biased, and as I've indicated, and I think that's a common truth, it's very hard to imagine that you're going to have many situations where missing completely at random is true. So even while that looks good for the CC analysis, yes, but it's unrealistic, and don't forget, it's inefficient. We don't talk about inefficiency in this slide, but that's still a consideration. But the most striking expression is this one. Under missing at random, you have a hell of a bias expression under last observation carried forward. That is difficult to interpret, isn't it? So if I'm asking you, give me a good solid interpretation of that bias expression, I can only see two very simple things. It's a long expression, and it's full of pluses and minuses. About every parameter, everything you see here and there is filtering into that expression. So it's a cocktail of sums and products and differences. I have no idea how you could get sensible conclusions out of this and even understand whether the bias is typically positive or negative. Sometimes it's quoted that LOCF is, yes, it's biased, but it's conservative, meaning you protect the null hypothesis a bit too much. Well, I'm not sure that's a good thing in the first place. I'm not sure that a liberal bias is a good thing in the second place. But the best thing is, of course, an unbiased result. But we cannot even say something about the bias. So throughout the pragmatic literature, the empirical literature, you will see that LOCF leads to all sorts of biases indeed. So the bottom line is, forget about it unless you would not have anything better, but I'll tell you, we do have something better. And that better thing will be the ignorable result. So for that, we will now switch to the ignorable result. So in the subsequent web lecture, ignorability will actually be shown. I've already used it earlier informatively, but I think also informally. So if we have it solid in our toolbox, we can start using it to the fullest.